While considering the case of fluctuating loads, we have seen in our last class lectures the fatigue diagram, and there we focused on two lines basically. One is the modified Goodman line, which checks fatigue, and the other one is the Langer line shown in blue here, which checks yielding. Now the procedure was to find sigma A and sigma M, and these are fully corrected by using the fatigue stress concentration factors and then plotting them here and then finding out whether the point is safe as far as yielding as well as fatigue is concerned. Obviously we didn't actually plot the points here, but we used equations, and the equations used were these on the left hand side. These equations for Langer line and the Goodman line, these are for these respective lines, while the equations on the right, these are the design equations, and these feature the factor of safety, n by for yielding and nf for fatigue. And we just put our values of sigma A, sigma M and strength values, and we figured out the factors of safety with respect to both fatigue and yield. Now we had mentioned earlier that the modified Goodman line is a conservative line in that it passes, this is a lower bound, it passes through below most of the points of failure. Now these are the points of failure, these are the points where the material has broken, which means that there is no infinite life. Now obviously some points will always be here, because in statistics you can never have a line below which there is no point, but most of the points are above. So this was a conservative line. Now this is not the only line used in design. For example, there's another line which is called the Soderberg line. Now this was Goodman line, Soderberg line, and this line joins the endurance limit with the yield strength SY. Now this is even more conservative than the modified Goodman line. But the principal advantage of this line is that this is the only failure criterion in which you don't need to consider the Langer line, because this at no point the Langer line intersects this. So you just check for the failure through this line, and if it doesn't fail, then there's nothing to worry about. But its major disadvantage is that it's way too conservative, so it's very rarely used. But thinking along the same lines, if we were to find the equation for it, it would be SA over SE plus SM over SY is equal to 1. This is for the this is the equation is for this line. For design purposes, we have to incorporate the factor of safety. So NF sigma A over SE, we just replace SA by NF sigma. This is the same procedure that we did last time. NF sigma M over SY is equal to 1, which means that S sigma A over SE plus sigma M over SY 1 over NF, or NF is equal to 1 over sigma A over SE plus sigma M over SY. The form is the same, but the difference being here you have SY and here you have SUT. But and here you don't need to consider the Langer line. But the downside is this is way too conservative. Therefore, hardly ever used in practice. But you find this in literature, so you should have an idea what this line is. So let's label it here. This is Soderberg line. Now, practice has shown that instead of straight line, we have only considered straight lines as yet. Uh, Practice has shown that instead of straight lines, curves are better as far as representing the true state of affairs is concerned. So, if we consider that even this, leave alone Soderberg, even this modified Goodman line is quite conservative, then the solution is that we've modeled this by using a curve instead of a straight line. So there are two curves that are often used. One of the curves is, and this is called ASME-elliptic, and this curve joins this point SE with SY. This is ASME-elliptic, and the equation for this is, because it's an ellipse, equation of an ellipse, so let's write down here ASME-elliptic. The equation for this line or this ellipse will be SA over SE square. This is not a linear equation. SM over SY whole square is equal to 1. So we are again using the same, like the Goodman line, SA over SE, SM or again for Goodman line this was SUT, here it is SY, so this SY replaced, but we have square on both the quantities. So this is the equation, and for design obviously we need to have factor of safety incorporated, again replacing SA by n sigma A and SM by n sigma M. And obviously if you let's write F here to differentiate this from the yield factor of safety, and if you take this common, then you have NF is equal to 1 over sigma A over SE square plus sigma M over SY square. This is your value for fatigue factor of safety. Now, practice has shown that this gives you a better design than the Goodman line, which is too conservative. There's another curve like the ASME-elliptic, which joins SE with SUT, and but this is a parabola, and this is something like this, and this is called Gerber line. Actually it's a parabola, but we call it Gerber line, and the equation for Gerber line, actually it's a parabola. The equation is, the quantities are the same as Goodman line, SA, SE, SM, SUT, because we start and end at the same point, but the difference is that we have a square on one of these. SA over SE, this is the same as the modified Goodman line, plus SM over SUT is a square here because it's a parabola, is equal to 1, and replacing for design, this is the equation for all the points on this curve, but for any other points inside with a factor of safety, just replace SA by n sigma A and SM by n sigma M, and you have this, the same procedure that we have been following. Now this is slightly cumbersome because you have in the same equation you have n and then n square, so it takes a little bit of solving, but it can be done, and it can be shown that NF for this turns out to be, it's somewhat lengthy, but and you don't need to learn this by heart because your textbook has it. You can refer to your textbook for this expression. In fact, the three most commonly used failure criterion, the modified Goodman, the Gerber line, this one, and the ASME-elliptic, this one. Uh, the important quantities of all these you can find in your tables 6.6, 6.7, and 6.8. And the important thing to note about all these is that all these three criterion, for all these three criteria, you have to also check the yielding. The fourth one, apart from these three, there's a fourth one, and we have seen that was Soderberg line. That uh, doesn't require checking for Langer for this yielding, so that can be used alone, but because it is way too conservative, we don't use that. So all the other three, 1, 2, and 3, they must be done, but whatever you choose to do, but later on you have to check for yielding as well, because in all these three there is a possibility that fatigue won't take place, but first cycle yielding might take place. So this is how some of the other approximations go. Again, this is just a matter of approximation. Some designs will be more conservative, some will be bolder, and there may be an element of over design involved, but these are the three criteria that are most often used. Now let's take a problem to demonstrate how one of these three criteria are applied to real world problems. Now this is a familiar problem for you. This in the last class we had done this for modified Goodman criterion. Now this is exactly the same question, except the fact that now we are supposed to apply the Gerber criterion and find out whether it is safe or not. So I won't go through this whole process again because we have all the values already with us from our previous problem, and I'm just going to calculate the factor of safety directly, and factor of safety will be calculated using this expression that we have just seen, because the Gerber criterion, this is the expression we need to use, and we have all the values required. Let's first write down the formula. 1/2 SUT over sigma m square sigma a over SE minus 1 plus 2 sigma m SE SUT sigma a square. Now we had calculated all these values in the previous problem, so it's just a matter of putting in the values. Please verify these values. We had done it earlier, so there shouldn't be a problem. And this is, if you calculate this, this should be 1.4. This is for Gerber criterion. Now if you recall, when we did the The same problem using the modified Goodman criterion. There the NF was 1.20, and that stands to reason because this is a because modified Goodman is a conservative criterion. This is the modified Goodman, and this is the Gerber one. So if a point, for example, lies here, then its factor of safety will be less as according to the modified Goodman criterion as compared to the Gerber criterion. Now the other part, the yielding factor of safety, that shouldn't change. It was 1.51 and it should be 1.51 here also because nothing has changed. Now this, if shown graphically, this turns out to be something like this. You have this is SM sigma M, this is SA sigma A axis. About 75% of SUT is SY. I'm just drawing it on a rough scale, and you have the same SY here, and half of SUT is roundabout SE. So this was your modified Goodman line. This is your Langer line. And the Gerber line is here. Now your point plot somewhere around here. So what happens is this: you join it like this, and if, like the last problem, if you see the modified Goodman line, then the factor of safety is 1.2, and then the factor of safety with respect to yielding is 1.51. So there's a fair margin here. But now because we're considering Gerber line, now this same point plots here. So the factor of safety with respect to fatigue for Gerber line, this is a bigger one. We just saw instead of 1.2 it's 1.49. But the other aspect of it is that the difference between the fatigue factor of safety and the yield factor of safety is not much here. The margin has reduced. So this fatigue occurs first, so it will govern, but very soon after yielding also occurs. So this is the whole situation shown pictorially. Now there's another part of this problem again which is not valid here, but it could be valid in some other problem. If infinite life is not predicted, here we have infinite life, but what if this NF was less than 1? Then that would have meant that there is no infinite life. So if infinite life is not predicted, estimate the number of cycles to failure. Now again we'll go through a demonstration procedure. We won't plug in the values because in this question there's no need to do that. But let's say this is our, again, SM sigma M, SA sigma A, and you have this is SUT SE, and your Gerber line is something like this. If your point had plotted inside, like we have found that it plots inside, then there's no problem, it's infinite life. What if the point had plotted here? No infinite life. So in that case, again, we need to find out how many cycles it lasts. There's no number of cycles on this graph. So what we need to do is again join this via a parabola similar to this parabola, but now it will pass through this line which lies outside the safe regime. Now this, the equation for this one we just saw, for this line, sigma A over SE sigma M over SUT square is equal to 1. This is for this line. What about the equation for this line? Because we are interested in finding sigma completely reversed, because on this axis sigma m is equal to 0, so whatever stress here is, and this is called the equivalent completely reversed stress with the same fatigue damage as our fluctuating load case. Now this system is a fluctuating load system, but when you extrapolate it and read the value from here, this is value of sigma a, which is completely reversed because on this axis sigma m is equal to 0. So for this line, this same equation should become sigma a over sigma rev plus sigma m over su. This is again a very familiar process. We have done this for the modified Goodman line. Sigma a over sigma rev is equal to 1 minus sigma m over sut square. Sigma completely reversed to sigma a over 1 minus sigma m over sut square. This is how we find this value. Once you have this value, again, just to repeat the point we had discussed last time, this is your SN diagram. You have revert to your SN diagram because we need to find out the number of cycles. This region from 10 raised to power 3 to 10 raised to power 6, this is the finite life region. And this sigma rev will be greater than SE. Obviously, if it was less than SE, then it would have, this line would have passed somewhere around here, and then this point would have been in the infinite life region, but it is not. So this is your SE. So your sigma completely reversed will be above this. So you just go there and read it, the value of n from here. Again, we don't plot this, we use the familiar expression with A and B, very easy to calculate once you have all the strength values. This example demonstrated the use of the Gerber criterion, but you can do the problems concerning ASME-elliptic in a similar fashion. Thank you.